In machine learning, feature selection is the process of choosing which inputs we should use when creating a model. In a more traditional machine learning setting, we might be working with a dataset like this, a set of features describing the housing property along with the associated prices. A common machine learning exercise is to create a model that can predict the housing prices based on a set of input features. One of the first tasks you might do is figure out which of these features matter and which don't. For example, the size of the basement might not matter at all in this prediction model, so we can leave it out entirely. Removing features allows us to simplify the machine learning model, which means less computation time for both inference and training. But when we start talking about embedded systems, this becomes even more pronounced. Usually when we talk about features, we mean sensor data or something derived from sensor data. And if we can reduce the number of features, often we can get rid of entire sensors. That means less PCB space. It also means fewer components on the board, which can save us costs. And it means less energy needed to power those components. When I made my perfect toast machine, I just threw in as many gas sensors as I could get my hands on just to collect all the data I possibly could to train a machine learning model. However, that being said, I probably don't need all of these sensors. If I could remove even a few of these sensors, it would simplify my whole design. If you're working on a real embedded machine learning product, doing feature selection would be an incredibly important step after, of course, you've prototyped the design to make sure it would work in the first place, as feature selection would allow you to reduce the number of components as well as simplify the model you're working with. I'm going to show you which sensors I was able to remove from the toaster project and still have it more or less work. But first, let's start with a simpler example of feature selection. There are a number of ways to do feature selection, and it is still an active area of research. Note that feature selection is related to dimensionality reduction, which is where we use some math to compress the features while losing as little information as possible. Such compression can be useful, but it often means more computations prior to the actual machine learning part. However, in feature selection, we figure out which features actually matter and drop all the rest. We might lose some information, but it's a fast and easy way to save on computation. Or in our case, save on the number of physical sensors we need. Feature selection can be broken down into two categories, unsupervised and supervised methods. With unsupervised methods, we look at the data without considering the output or target of any machine learning model. In other words, we analyze the data as it is. One popular unsupervised feature selection is to take the correlation between each of the features or channels. By looking at the Pearson correlation coefficient, we can quickly see if any of the features are linearly dependent. That means there's redundancy among the data and we can often drop one or more of the channels. There are other techniques that look for nonlinear relationships, but I won't go into that here. Next, we have supervised methods that usually require training a model. The output of that model, which might be a regression or classification model, is used in determining the importance of the input features. The supervised category can be broken down even further. Intrinsic methods are feature selection processes that occur naturally whenever we train a model, and we can look at the model to determine which features it thought were important. For example, the technique of adding an L1 regularization term to a loss function is known as least absolute shrinkage and selection operator, or LASSO. We can then look at the weights of the resulting model to determine which features it thought were important. Filter methods examine the relationship between the inputs and output of the model. One such method is the chi-squared test. Finally, wrapper methods like recursive feature elimination, or RFE, train many models while slowly removing some features to see which models work the best with fewest features. You could spend an entire college course just talking about the different feature selection methods out there. For this video, I'm going to focus on unsupervised correlation and lasso to try to figure out which features were the most important in my toaster project. I've put together a quick demo to demonstrate how these feature selection processes work. We'll be using the iris dataset, which is a very common, very simple machine learning dataset used to usually practice with. It just contains sepal length and width and petal length and width. And the idea is we want to identify different iris species using that data set. So I'm going to load that data set and I'm going to go ahead and split it into test and training sets. We won't be working with validation sets here. Notice that I've set aside 50% for the test size here, and I'm using stuff from scikit-learn to help me do this more quickly. Next, let's take a look at this data. So you can see here we've got the feature names or channel names, sepal length, width, petal length, and width. Here is an example from those. These are given in centimeters, and then the one-hot encoding for the species output. Next, we can plot the data, so you can kind of get an idea of how these dimensions work to identify the different species. Hopefully from this, you can see that petal length and width gives us a much cleaner delineation between the species, where sepal length and width are a little messier. Hopefully from this, you get an intuitive feel that petal length and width provide a much better feature set for delineating the different species than do sepal length and width. We're going to explore the unsupervised and supervised methods for doing feature selection to see if those line up with what we expect here. First up, we're going to examine the relationships using correlation. I won't go into the math behind correlation, but there are some really slick tools from Pandas as well as scikit-learn just to spit out correlation plots for us. Note that it's mirrored along this diagonal axis, so this chart looks the same as this chart, it just might be rotated. And what we're doing is we're comparing sepal width to sepal length, and then if you compare sepal width to sepal width, that correlation is always 1. They are exactly correlated because it's the same grouping of data. So instead of plotting the correlation, which would just be a line, it gives us a histogram showing how that data is distributed. A diagonal line or straight line means that there's a linear correlation between petal width and petal length, meaning you can probably write a linear equation that takes in one of the features and uses it to output another feature. That means that feature is redundant and we can often drop it. So petal width and length, you can see there's decent correlation here, not so much for some of the others. Note that in the toaster project, there was just a straight line for pressure, or 2 straight lines for pressure, which meant that pressure never changed, which I wouldn't expect it to considering I didn't change elevation or I didn't pressurize my house. So this is a great quick way to see if any of the data is redundant or useless to your machine learning model. Next, we can view the Pearson correlation coefficients. This gives us a value that describes the linear correlation between each of the features. And we can even do it as a heat map. So the closer to 1, the redder it's going to be. So you can see here petal width and petal length, which we saw earlier as more or less this diagonal line. Sure enough, that's pretty close to 1, which means there's a high linear correlation between petal width and petal length. And apparently same thing for sepal length for both petal length and petal width. Many times this means you can often drop these because they are redundant. Looking at this, you might think that we can use sepal width as our only feature, but that's not always the case. Sometimes you need the little bits of information that are encoded inside of the seemingly correlated features. So this is just a starting point for what we need. The other thing is the Pearson correlation coefficient only gives us linear correlation. You have to look at these charts to see if there's something like an x squared or an x cubed or some other correlation that's not exactly linear. Now, let's look at how we can use L1 regularization to perform feature importance ranking. First, we build a model that gives us at least decent accuracy for the task at hand. I'll use a neural network with 2 hidden layers and an output layer to predict the iris species based on the sepal and petal measurements. The arrows show how the data flows to the different neurons in each layer. You can assume that each arrow going to a circle or neuron has an associated weight that multiplies each value. There are also bias terms for each layer, but we don't need to worry about those. For a multi-class prediction problem, we usually use the categorical cross-entropy loss function, which gives an error value that measures the difference between the predicted value, y hat, and the ground truth value, y. To do lasso, we add an L1 regularization term to our loss function, which sums the absolute values of the weights in a particular layer, multiplies that sum by a coefficient, lambda, and adds the term to the original loss function. The training process will then try to make the loss function as small as possible while also trying to make the weights as small as possible. Regularization like this is often used to fight over fitting. Common values of lambda are in the 0.00001 and 0.01 range. However, we can make lambda a little larger, say 0.1, which will drive unimportant weights to 0. To perform feature ranking, we would apply this strong L1 regularization term to the first layer of our network. After training, features with more importance in the network will have weights with larger absolute values than features with less importance. I've illustrated this by showing the larger value weights with bolder arrows. From there, we would just need to examine which of the features have the largest weights in the first layer. Ideally, we could drop the features that do not rank as highly with little impact to our model accuracy. Of course, you'd want to test this by retraining your model with the new subset of features and revert to a more reasonable L1 coefficient. Let's try using this lasso method on our iris dataset. So I'm going to define a few helper functions here. The first just prints the history once we train a model, and it just gives us the history to ensure that indeed things are training correctly. Then I'll plot the receiver operating characteristic, or ROC curve. This gives us an idea of generally how good the model is, which is useful if we're not going to be deploying it to the field. We're just going to throw a test set at it and examine the false positive rate and true positive rate. From there, we want to generate the feature importance rankings. This is where we give it the model, and as we saw, we're going to get the weights of this first layer, which we can see here. We get the first layer and we get those weights. Next, we take the root mean squared of each set of weights. This means all the weights associated with one particular feature. We then normalize those scores so that ideally they all add up to 1. And then we're going to print those out in order of importance, along with those feature names. So first up, we're going to build the model, and it's going to be that 3-layer model that we saw earlier with 4 neurons in the first hidden layer, 4 neurons in the second hidden layer, and then our output with 3 nodes and a softmax layer. Notice here that we are adding an L1 regularization term with a lambda of 0.1, which is pretty high for lambda. This will hopefully drive those unimportant features to 0. Now that we have our model, let's try training the model, and we will give this just a moment. With our model trained, we're going to plot the history and ROC curve. And you can see training did happen. The ROC curve gives an indication of how good this model is. The more of a right angle this line is, the better the model. The more this line is on this diagonal, the worse the model, because in that case it means the model could essentially just guess or roll a 3-sided die to determine output species. It's just a random guess. So the more area under this curve, or AUC, and the more that approaches 1, the better this model. So we've got an AUC of 0.996, so this is a pretty good predictor of those iris species. Next, we're going to print out the first layer weights, which you can see here. Here are all of the weights if you want to see the raw values, and then here are the bias terms from that layer. Next, we're going to score those features where it takes in these weights, and it's going to give us in order which features were the most important in determining the output of the model. In this case, we see that the petal width and petal length ranked highest, so here's the normalized root mean square of 0.7 and 0.25, and the sepal width and length did not rank very highly, which means that the model's really focusing in on this petal width and length to determine the outputs. And that lines up with our plots up here, where the petal width and length, sure enough, were better at delineating the different classes, where sepal width and length did not help us much. So going back to where we were, what we can do from here is, first let's list out our features. and these are in order. So we're going to drop some of these features, and we're going to drop 0 and 1. Since sepal length and width were not very good at helping to classify those iris species, we're going to drop those. And here are some others you can play with. So I'm going to drop those columns from our data set. And now our data set is 150 samples total between training and test, and only 2 features in each, which is our petal width and length. I'm going to use the same model as earlier, but notice that I'm setting the L1 regularization terms to 0.001, something a little more reasonable. So here's the new model, and notice that it has fewer parameters than what we were using for feature selection. And then we're going to train the model and test the output. Let's scroll down and we'll plot the history and ROC curve. And sure enough, this actually performs a little better than the above model did. But that's okay. You can see that even though we dropped petal length and width, we end up still having a pretty good classifier with fewer features. Now let's switch over to the toaster project. Here I have computed all the correlation values between each of the channels from that toaster project. You can see that there is some linear correlation between a few of the values and some nonlinear correlation between some of them. This doesn't give me a good indication, but maybe I can drop like VOC2 or NO2 or something and still get decent values. This is a good way to start identifying what might be redundant features, but the real kicker occurs when we start to use that lasso method. So I've trained a model just like we saw with the iris data set, and I've ranked all of the features. And we can look at these, and it looks like the model really likes to use probably about half of these, a little more than half, where temperatures used a good bit, humidity not so much, but I think there's a relationship between those as we saw in the correlation plots. And it looks like NO2, carbon monoxide, VOC2, I guess ethanol is down here. So those 4 belong to that multi-channel gas sensor. VOC1 and equivalent CO2 belong to the SGP30 sensor, which means we could probably drop that sensor completely. And the other thing I notice is that ammonia does not rank very highly, and that's its own very expensive sensor, despite supposedly being very useful to identify burning smells. So I am going to try to drop the SGP30, and I'm going to drop the ammonia sensor, but leave the other 2 sensor boards on there. That should reduce my component cost. I've trained some models down here just to see what works and what doesn't. And keep in mind that you can always iterate on this process where you remove some of these features, train a model, see what works, maybe try adding some back in or removing others, and you begin to learn which features really are important. And note that it might mean collecting new data or trying a different model architecture. Eventually you get to a point where you know which features work the best and you can probably drop the rest, which is what happened here. So over an edge impulse, all I needed to do, since I'm keeping the same model architecture, I just removed the CO2, VOC1, and NH3 channels, and I've kept the rest. That means I can get rid of these 2 sensor boards when I go to deploy this model. I've trained it already and deployed it so it's ready to go on my WIO terminal. I've uploaded the new program to the WIO terminal, which means I can disconnect all but the multi-channel gas sensor board and the BME680. And now it's time to test. I've got a piece of bread here that I'm going to put into the toaster and start the process, just like we did in the previous video where we made and tested this whole perfect toast machine. Note that I didn't collect new data for this. I used the same data, but I trained a different model. If you're doing this for real, you may want to consider collecting new data and then training a new model, simply because now that we're working with different sensors, it may adjust how that model trains. But for now, let's see if this works. Ooh, all right. Ha! It still works. Look, look. It still works. I cannot believe that still works. Or rather, we totally predicted it will still work based on our feature selection process. So I hope this helps you get started using feature selection to reduce the number of sensors in your project if you're working with embedded machine learning. With that, good luck and happy hacking!